Okay, see, today we are going to continue the discussion on added resistance in waves. What I mentioned at the end of last class is that when you have a ship traveling in waves, there is a additional resistance, you can call it, that comes when the ship is moving forward. See, I was mentioning that this added resistance hydrodynamically arises mainly because of the fact that the ship undergoes heave and pitch motions and it creates waves, but that is not the only thing. I was also mentioning that this is actually hydrodynamically a second order force. In fact, if you were to think and imagine the force time history, this additional force time history, you would expect it to be an oscillatory. The only thing that happens is that this oscillation, if you average over time, would have a mean value. This mean value is what is our mean added resistance. What I meant is, just imagine the ship is undergoing oscillation. Obviously, we mentioned this, that in an oscillatory body, when the input itself, the incident wave itself is oscillatory, every response is oscillatory. Even the force that you measure would be oscillatory. The only thing that happens is that if I were to take a time average over a long time, this oscillation is not having a zero mean, but has a steady mean, and this is what we are called mean drift force, mean second order force, which is same as mean added resistance for a forward ship. Now, having said that, I will just dwell a little bit on the reasons behind that. It turns out that if the ship is subjected to large heave and pitch, okay, in mostly head waves you would expect the added resistance effects can be broken down to three different effects. One of them would be let me write it, then we can discuss it more. Experienced by the ship forced to oscillate in calm water. Thus, see, it is important, the reason I am writing is because remember what is our objective? Our objective would be to determine, estimate, assess, whatever, find out this quantity. So, I would require to come up with some formula, just like in resistance. To do that, I need to know what are the components that might consist, that might compose of this force. Then I can have an estimate for the various components and add it up, whatever. This is of course what we have told earlier. I will come back to this. Let me first complete writing. Phase shift between reflection and okay. Let me now, that we have finished writing. Now see, first one, suppose I were to plot in some means, by some means added resistance against frequency. Obviously, frequency is wave parameter, isn't it? Like RAO. It will basically may look something like, it will have some variation. Now what happens? See, now we will just look at that. If you are looking at very low frequency, let's look at the other way around, high frequency, somewhere this side. Okay, what does high frequency mean? High frequency means waves are short. So suppose I take a very large tanker, waves that are there are very short, not this short but some short. What would happen? You would expect in this that the ship doesn't even have a motion, very less motion. Rather, these walls of this hull will act as if they are just like a wall, and the incident wave comes and hits and gets reflected back. See, it is, if you take a very large ship in a very short waves, small waves, the entire hull would not even undergo motion, but the waves would come, and mostly you know that in waterline part the hull is vertical, it will act as a wall and get reflected. But it will also create a mean steady force. Then what we are looking at is force in this region, that is given by this effect, that is resulting from reflection and refraction of incident waves. Now mostly of course is this range where the ship is undergoing motions, heave and pitch, which of course gives rise to radiated waves. And remember, damping, the word damping term actually represents the radiation wave energy. So essentially, just like in our wave resistance, this energy of these waves that are getting dissipated has to be coming out as resistance, which is what I mentioned yesterday. So this part is given by this, and there is of course one more reason, this is difficult to explain, but this also arises. So having said that, see, we will have to come with certain empirical formulas. This is a second order problem. As I mentioned, this force is a second order mean problem. It is not very easy to solve, but it is very important because everybody wants to know how much is the additional resistance that is coming, which would cause the ship to slow down. You need to know that, you need to estimate that. It is a primary quantity of interest for a ship design, because after all you have to know, since you are, when you are going from A to B, you are always going in certain C state, and therefore you are not making the 20 knots or whatever you are designed for calm water. How much you are going to lose, or what is the extra energy you need, power. Okay, we will come to that, but there is another a few points I want to say, that certain observations on added resistance characteristic. Okay, before we go back to these formulas, now we normally consider head C because it is a head C that you expect maximum heave and pitch and maximum added resistance. In fact this is very interesting, because you see the vertical plane motion are maximum in head C, and you know we mentioned earlier about spectrum. In head C the transformation of spectrum absolute to encounter, there is no problem. The problem that arises always all this singularity in following waves. But it turns out in reality, at least this is one good thing of sea keeping, that the head C, which is more important, I don't have this problem of that following the singularity in SW and all that, zero negative frequency, zero frequency and all this stuff. Anyhow, having said that, this is of some of the observation. RAW, it turns out, is fairly independent of still water resistance. say this is of course good or bad news, we do not know, because had it been a percentage it is different, but it is not a percentage, which means in some cases it can slow down very much, because it does not really have, suppose there is a ship designed for a low speed with a low still water resistance, RAW may be a very large percentage. It is proportional to a square. This of course we know that it is proportional to a square regardless of ship motion, regardless of reflection, is an energy. It turns out that pitch motion is very significant, even more than heave motion, as far as actually this reflection that I said is relatively small, that is this high frequency part. In fact, that is what happened. In fact, this high frequency part, this graph typically comes down. So, you know, like the values, larger value of added resistance occur because of the motion. Now, this is another important. The maximum see, this is actually just another observation, that if you understand that if motion is larger, you of course expect more resistance, right. Now, in pitch resonance period, you are going to have a very large pitch. In heave resonance period, you are going to have very large heave. That is of course one of the reasons in the design you do not want to make, you do not want the natural heave and natural pitch period to be same. If it is same, you have a very bad motion and very high added resistance sometime, but this only says, remember that the encounter period changes depending on the speed. So, suppose that at a given speed I have a pitch resonance, normally what would happen, maximum RAW will occur at a higher speed than that. That is what it says, it is a general observation. Anyhow, these are just general observation. Now, let us come to certain formula for that. Now, we can understand that there is no general formula that caters for added resistance over the entire range, because what we have seen at higher frequency, which means if lambda by L, wavelength per unit ship length is much smaller, maybe half or less, then there is much more reflection, and it is dominated by this third phenomenon, reflection. But we have also seen that this is actually small value. So, most of the formulas that have actually been proposed or are used is for this region, that is for the motion part of the region. That is connect, and therefore all this empirical formula you would expect will be related to number one, heave damping, pitch damping, heave motion, pitch motion, basically heave and pitch phenomena, which would be in terms of exciting force, radiation force, etc. So let's look at some of the old formulas and progressively newer formula. One of the older formula, one of the old one, most very old one, it shows like this. I just want to say little bit of that. And unfortunately none of them are very validly good. See here, this is exciting force in heave, amplitude of exciting force in. Obviously this is going to be amplitude of pitch exciting moment. This is, we can make it out, ZA, amplitude of heave motion, theta A, amplitude of pitch, EZF, phase of heave with respect to exciting force, and same pitch exciting moment. This is one of the old formula. See, what I wanted to mention here therefore see is that suppose I have to estimate it. If I use this formula, what happens? I require to find out heave exciting force, pitch exciting moment, heave amplitude, motion amplitude, pitch motion amplitude, and the phases, which essentially means I am solving these heave and pitch RAOs and all these parts I get. So you may wonder here why in this formula I don't have explicitly heave damping and pitch damping, because after all damping term represents the energy of this dissipative wave. The reason is here actually in hydrodynamically exciting force and radiation force are related to each other. In fact, the damping force is the information of that is embedded in this Fa and m theta, this parts. What I am trying to say is that look at the hydrodynamic principle point of view. Here I have which added mass and damping force, which is called basically radiation force. That is, if I took a calm water and oscillate a body, then the wave that it gets created, the force connected to that. Then I have got an exciting force. If I hold the body fixed, an incident wave gets reflected. Theoretically, these two are actually related. In any case, there is no point of going through several theories. Another formula, this one is better in terms of, see, this looks like omega E cube by 2g. This is what, these are all simple formulas. Now here I will not probably write, but Bz, B theta are heave and pitch damping. Okay. Za and theta A are heave and pitch motion amplitudes. Omega E, of course, we know. Now, I forgot to mention here that here this k is basically wavelength parameter or frequency parameter. That is, the wave number. So omega square is gk. That is this k. Omega square is gk means omega square is gk. No, that omega square is gk. So k is omega square by g. Essentially, what I am trying to say that the information of the frequency is embedded here, and all of them has to be for that particular frequency. See, this is for a given frequency, given wave. These are all regular waves. There is a single regular wave of frequency omega e or number k. For that, what is the RAW? That's what we are talking. We are not yet talking about RAW in irregular waves, which we will talk eventually. So this is like that, this formula. There are other formulas. So I will just write one more and then the final one. So this one, as I mentioned, explicitly uses damping, motion, and this damping is a term that actually contains the information of the wave that the body creates. Then we have another formula. Maybe I will just write this one very quickly. Non-dimensional form, this is given rho g a square b square by L. It is given something like L square. This is only to give you some idea regarding in terms of RAO here. Let me just write it down, then I will explain to you the physics behind it a little bit. And P3, let me just write up to this much then. And other terms are there, like epsilon is some phase angle. Again, you will see what you will see here. This is again a combining heave and pitch motion. ZA by A is nothing but heave RAO. So it is heave RAO square, exactly same as what we have got ZA square. If you look at the form, what I am trying to say, look at the form, look at this comparison. ZA square is amplitude of heave square, which is nothing but embedded here. P1 is a term which is a function of B33, that is heave damping, which is exactly here, Bz. Okay. Now theta A lambda by 2 pi A, actually theta A by A is nothing but pitch RAO. It is nothing, the reason why it is written theta A lambda by 2 pi A is basically to make it non-dimensional, that is all. Essentially you are dividing the slope by Ka rather than actually theta by Ka. You can see this theta A by 2 pi by lambda A, where k is supposed to be this wave number. Now, so this is same as this term. P3 is nothing but the term equal to B55, exactly same as B theta. The only thing that modification that has happened here is that it has taken a combined like action theta heave and pitch, something like heave plus x pitch square, which is why there is a term that comes out like when you do A plus B square, additional term heave pitch, one can call this a heave pitch coupled term. So the form of the equation looks somewhat similar, and however, I tell you the most common and the most used form that today is used is none of this. It is this one, the one that I am going to write now, but that is slightly more difficult to compute. This one says RAW is equal to pi by, this part of course we do not worry, but it is integration of Bx into, I will write in this form. Now what, see this form is basically derived based on energy balance, that is the energy of the waves that has been created by heaving and pitching motion, and relating that with wave resistance. See here what the terms are is like that. If I take a shape here, take any section at x, this part is going to be my vertical velocity of the section. B33x is the sectional damping coefficient, two-dimensional sectional damping coefficient. A33x is sectional added mass coefficient. What you find out is that I require to have, therefore, if I want to use this formula, I actually have to have for each section added masses along the section known, damping should be known, and I need to find out the slope of the added mass curve. So therefore, applying this is slightly more complex. The reason why I am saying that if you look at this previous formula, all I needed was added damping, there is no added mass actually, only damping, but for the full hull. Okay, whether you call this or whether you call this. Of course, if you call the first one, you need exciting force. As I said, exciting force can also be connected to added mass and damping. They can be related. But never mind, let us say this too. But in this form, which is actually more, people think this has a better fit, and this is what is recommended today for using. It's a little more complicated to use. Why? Because you need to find out sectional added masses first, and then you have to find out this sectional added mass, you have to also find out the relative velocity. Remember that this velocity here, this contains both heave and pitch. So my heave is there, pitch is there. In fact, I also have eta, because there is a relative velocity with respect to water surface. So I have heave here, pitch here, just like those things I had. So this one, what we find out is that all the formulas involve necessarily heave motion, pitch motion, and the phase between them. Remember, if I want to do this, I also need the phase between the two, what we have mentioned yesterday. So I need heave motion, I need pitch motion, I need heave damping, I need pitch damping, I need, well, in this case, why it is actually no pitch damping, because in sectional case we have discussed earlier that sectional vertical damping into x square gives you pitch damping. No, A55 is nothing but x square A33 integrated. So essentially, when I do sectional damping, I have only sectional damping in vertical, that is A33 and B33, small A33, B33, which basically A33, B33x, this gives rise to me B33 as well as B55. What I am trying to say is that therefore, the information content is all same, but how do you make a formula is different, and that depends on different physical approximation that is used. Okay. So you therefore will wonder which is correct. Why there are so many formulas? The reason is very simple. Because a second order part you cannot calculate. You just cannot calculate. In fact, if you look at RAO also, you will make various kind of approximation. But these are the kind of formulas for added mass. Okay. So having said that, typically what I will now I am going to tell is that now see you calculate that for different whichever formula against omega E. Now normally what would happen, you will have some non-dimensional form. So you might make it L by G. And here I have got RAW, but RAW is proportional to A square, so you put A square. But you know this is not non-dimensional, so normally you non-dimensionalize. For example, it might be rho G A square into B square by L. I mean this extra part is just used for non-dimensionalization, that is this part. See this and this you are using for non-dimensionalizing, and typically you will be calculating that using any of the formula, and they will look something like this, you know. Etc. That depends on various you know like fruit numbers as you go to speed. Higher the speed, higher the resistance, etc. You end up getting this. So this tells me therefore average added resistance, okay, in a single wave, or you can say RAO for that. Having said that, our next job is that how do I find out mean added resistance in an irregular wave, right? See, these are regular wave, which means if I have this wavelength, this, then I know what is for this particular speed, what is my add. After all, added resistance is a function of omega E. You can say also speed. Actually, you can say omega is ambient speed, but we normally do it separately because same one can occur for different combination. So essentially so, right. So this is like an RAO, but the question is that now next is that how do I construct or how do I determine added resistance in irregular waves. So for that we do that. Remember, I need to have a spectrum. So I will just try to tell you this, that see, added resistance is proportional to A square. So therefore root over of RAW runs to A. Now you remember that when I did a spectrum of any response, okay, what was it? It was the response amplitude by A square into wave. That's what we did. Why? Because response RA here was proportional to A. Remember what is RA? RA was response amplitude. See, when we did all these things so far, all the quantities like basic motions, accelerations, relative motions, whatever, that this part, this response, we said it is proportional to A, means it is linear function of A. Okay, that is why I could do that. But here problem is that this is not a linear function, this is a function of A square. So what we have to do therefore is that it's very simple though. A's added resistance becomes simply, you can say, see, it has to be proportional to A square of the quantity. So this becomes simply RAW root over by A square of that into SW, which gives you nothing but which makes it simply RAW into 1 by A square into SW. In other words, this becomes my function RAW by A square. I'll come to that. That means this is my equivalent of RA square, not RAO. See, remember once again, if you look at that, this part, what is this? This is nothing but this root over of RA, root over of added resistance by A square, root over of that, which means now coming to this, if I have a spectrum formula, I have here S omega, then here I have to have, remember here RAW by A square. This is what I plotted. Remember, this is what I plotted here. That is what I have done in a non-dimensional form. If you just take that, see, I have plotted here. What do I plot? I always plot RAW by A square, because RAW is proportional to A square. So, in other cases, what would I have plotted? Resistance amplitude, not resistance, response amplitude by A. But here I am plotting this by A square. Remember, this is the most significant difference that one have to remember. So, I am doing that, and now I get this spectrum here, that is S added resistance, this thing. But here remember, in this diagram, A, B, C, yeah, C equal to A into B compared to A B square. This is very important for us to realize. That means S added resistance at omega E, let me put it omega E only, is becomes essentially R A W by A square into S wave omega E. Okay. This is very important to understand. Now, there is one more point to that. I find out this, but you see here, we are not interested in this spectrum to find out what is my 1/3 significant value, what is my 1/10 significant value, etc. All that what we want to know is mean value of added resistance, or average value of added resistance. So, what is the average value? The average value of added resistance, or maybe we can do it here itself. If I integrate this d omega, then I call it m0. Okay. Then average value, that is by formula 2 m0. Remember, not 2 square root of m0, but 2 m0. I will write it down properly. You see, remember, not 2 square root of m0. See, in any other responses, it was 2. What has happened in compared to that other? If it was in another response, typical response, it was 2 square root of m0. Square root, because it was proportional to A. This is proportional to A square, that is why 2 m0. So, this is what you need. This is what you need. See, then what happens is that you will calculate for various C state these added resistances, and they will try to, like average value. So, what I mean, ultimately what you will do is that, say here a C state, say 3, okay, speed, mean value of RAW, it will of course look like something like that. Then of course this is maybe some C state, so it may look different C states. Understand what? See, what we have done therefore is that, see, in actual calculation you would do the reverse way. You would be determining therefore the added resistances. You will consider different speeds. Say, let us say you take 10 knots, 12 knots. Say, let us say you take 10 knots. Okay. So, for 10 knots I will find out added resistance, or rather the other way around, I will take a particular C state, say C state 3, then I will find out what is my mean RAW at 10 knot, 12 knot, 14 knot, 16 knot. I plot them. Then I will repeat that. So, I will end up getting this. That means you are getting all the points from the spectrum again. So, you see these calculations are done like that, you end up getting therefore speed versus RAW, etc. But mostly people though they do not use that way. What they will try to find out is the other way around, try to instead of RAW you will try to find out V versus effective power, which will of course become similarly the effective power that you need go like that for different H1/3. This will be of course different C state. What I am trying to say, you see that this you can translate to a speed loss sometime. That means you will say here H1/3 significant wave height, here V, and depending on the thing the speed loss. This will maybe at particular angle, you know, like I will explain the meaning of this. See, it is a question of how do you use these diagrams from the actual practical point. Once again, what would happen is that we are finding out average added resistance in a given C state from the RAO of the added resistance. That means first of all I calculate the, you can say RAO or you can say regular regular C added resistances. So I calculate these points, these points. This of course is a function of shift speed, this is also a function of heading. Let us say we take head C mostly. So for a head C for different speed I have done this. Now having done that for a typical, for all those speeds I will also come back to this and I will find out RAW average in that particular C state. This is my C state, this is my added resistance in regular waves, combine that I get this, from there I get this. So I have got this as a function of C state speed. Now I can plot them against speed versus this, whichever way I want, whether I can do C state versus this for different speeds or other way around. Normally this is more beneficial, but instead of RAW you can also relate that to effective power. Similar kind of graph you will get. Then conversely I can find the speed loss, because what will happen if my ship power is this much, I will know that I will make this speed. See, suppose I am going at 20 knots and my effective power is so and so and my engine is giving so much power. So I can conversely find out available power is so and so, therefore what speed I will make in a C state. This also can be plotted in this way, that means C state versus initial speed, with that how much speed reduction comes out, that reduction of speed. You can also plot it. In fact, this is what is ultimately used more, because you would like to know not how much resistance increase or power increase, but for the given power what speed loss you have got, because the reason is very simple, I cannot increase my power, I am actually running at the full power. So therefore I want to know how much. So this is what is called speed reduction. Again, this is a function of course, see here I plotted this, but you can plot this if you want to do the more calculation. You can calculate this speed loss as here, you know, this is as say H1/3, this is actually a C state, this is the initial speed V, and this may be at head C, this may be at 90 degree, etc. You can also do that for different heading angles, although this is most important, but you can also do that for. So when you start at 20 knots, so when I start at 10 knots, again I will have graph like that. So I can have these graphs. See, what it means is that this would be, supposing I start from say 15 knot, then this is my, as the C state goes up, my speed reduction comes to this corresponding to 180 degree heading, that is one head C. This would be the speed loss in 90 degree, etc., etc. You may say conversely that in the opposite side will be pushed up, but normally that is not taken. It is only the head condition that we take. So this is how we can calculate this added resistance, you know, this is a kind of part of added resistance. Okay. So to summarize added resistance, therefore, the only difference that it has got with other responses is it is a term proportional to A square, not A. So therefore, my RAO calculation is not same, it is not spectrum is not RAO square into this. Here I have to take simply a different way. Second thing is that in here I don't have much of statistical property of importance. I only want to know the mean value or average value. So these average of averages, remember even single wave, what added resistance is an average value, because it is an average mean value, and this is kind of average of averages. So there are a lot of averaging there, and you end up getting this. Okay, so this is what about, and regarding the calculation of added resistance, therefore, well, there are a number of methods, nobody knows, which is very good. As I said, the last one supposed to be more widely used today in practice, in industry. But for that you need to have a good program to determine sectional added mass and damping along the length. If you not, we can use some other ones, but there is always a debate about how close they are, etc., because computationally determining a quantity that is second order is always more difficult. Okay, I am going to now just change to another topic slightly, just in the next 5-10 minutes time, very quickly before we talk something else tomorrow. So I am now shifting to this something called motion stabilization, just basic ideas, because in short time we have some 20-22 hours for sea keeping. There are too many things to just mention. Nowadays it is becoming more important, you see. Everybody wants a comfortable ship, everybody wants to reduce motion. So there are a number of stabilization ideas that are coming, but I will not be able to talk about that. I will simply talk of roll stabilization first, just little bit. Now the ship is rolling badly. As you know that roll only goes larger, you don't expect pitch to go more than 5 degree or 2 degree. If it's went 5 degree, the bow would have come up. But it is roll which can go 10 degree, 15 degree, 20 degree, etc. So that's why people want to always reduce roll motion. So there have been much more talk on roll motion from beginning. Now roll stabilization can be passive type and active type. What is meant by passive? Means you just make an instrument and don't do anything, you just leave it. Now the biggest example of that is, of course, is basically bilge keel. The most common example is bilge keel. What you do in bilge keel? Simply put a keel plate here. What does it do? It essentially produces damping. Why? Because as it tries to rotate, you see, it will kind of act as a damper. In equation of motion, B goes up, viscous phenomena, because the damping occurs because flow gets separated. Now roll actually otherwise has a very low damping, because as you know, if I took a circle and if I just oscillated that, it will keep on going for a long time. Even if I put a bilge keel, it actually goes on a long time, and as a result what is happening, my resonance period, your roll is very high, you want to reduce it. So this is the most simple common type that is used, and it has been found out. The most effective one is to put, of course, at this bilge location, more or less along this line, because if it is CG here, it rotates about that, making a line like that gives the largest kind of a effect. Then of course there have been many other ideas. For example, there have been ideas of gyroscope. I will just mention some of them. Then there is idea of movement of weights. Then there are rudder action. People also sometimes use rudder. Rudder also acts as a stabilizer, because rudder is a plate. But let me go back to this side. Then here we have got passive and active roll tank. Actually you can say this is passive, so let me call it roll tanks. I will mention these roll tanks, and then of course here stabilize, actually roll tanks, and among the active we have got stabilizing fins, and there can be other ideas also. Now let's just talk these two things quickly, and then we'll this two. Basically, all this what they do, even weight and all. See, the idea is like that, which is same as this tank also. You have this particular. Let me just look at this little bit of this thing. You put a tank here, water tank. Water is here. Okay, what it does, I mean just the physics of it, there are a lot of other maths. As it rolls, see water also rolls, but there is a phase gap. Means as it is going to this side, water is still trying to go on that side. So that acts as a damping. What is happening? The forcing function, if the motion is like that, my water motion is delayed action. This is exactly what it does. This is the delay action, that is what is trying to act as a retardation. There is a phase gap between the motion when it has gone to the maximum angle and trying to come back, water is still going on this side. So that will always try as a damper. This is the same idea for all this principle of gyroscopic movement of weight, etc. That means you have a pendulum type of thing and make a phase gap between the displacement and the weight shift, and the weight is trying to hold you back. That because weight is following you, it is like when I kind of am fond of telling, it's like when you try to go in a mass somewhere group, you want to go out at some time, you'll see that there's always slowing down process because the whole group, last guys are trying to slow you down as a group when you go. See, this is kind of effectively like a slowing down process because you are being retarded, pulled back by somebody else. So same ideas are here, but why passive? Because you do nothing, you just make a design and it takes care of its own thing. Like for example this one, all that you have to do, there are a lot of calculations, is that you have to tune properly. So maybe that the water level etc. has to be adjusted depending on the kind of loading condition. Okay, so this is one. Now just the final thing is active stabilizer. This is now becoming very important. What they do, you have here fins, not throughout, in the particular hull, maybe there is a fin here coming out and there is a fin here coming out. These fins, this is of course active stabilization, because here depending on the response, how the roll, you have to control, you have to have a complete controller. These angles you have to keep changing, like it is like a, how should I say, it's a aerofoil section normally. So it's like the aerofoils are there, so you basically ship is going, as it rolls you change these angles effectively by a controller to minimize the roll motion. And this of course is used for pitch also, for heave also. Nowadays it is apparently very common to use. So active stabilizer, of course the entire part cannot be there, only a small parts, a small fin with a rod connected, and there is a mechanism that will control that. That means there is a feedback. You measure the roll motion, depending on the roll motion you change this angle of attack, that will give a counter effect that will reduce the roll. So these are kind of, and this is not I can only mention this briefly here because the subject of the control is a different subject altogether, active control. You have to have knowledge of control theory, but these are the things that are being used. Okay, so today we are closing it here. The last lecture for seakeeping part of the course will be tomorrow, where we will talk about design, the seakeeping in design. How do you consider seakeeping design? Should you consider, etc., etc. Okay, thank you.